Okay, so in the last video we talked about dividing polynomials, and when we actually divided those by some divisor x minus a, where a was just some number, we got some quotient q of x and a remainder of r. Because sometimes, obviously, when we divide, something doesn't go into another thing really nicely, so we get some remainder. And the reason I'm going over this now is to introduce this remainder theorem and factor theorem with polynomials. Now, when we kind of did this division, we represented our polynomial p of x as this divisor, x minus a, times q of x plus our remainder. Now, what the remainder and factor theorem do is they give us a really quick and easy way to check that if you divide a polynomial by something, what will be its remainder and its factor, or whether it'll be a factor, without having to do all of the laborious work of dividing through like we did before. Now, if we consider this particular term a, where a is some number. Because remember, before we divided, for example, by x minus 2, x plus 1, whatever. So this one was just some number. Now, to check what a remainder is, for example, we can say that, for example, when dividing for example by x minus 3, our remainder is p of 3. This is the output we get for an input of 3 in place of the x, thinking back to what we learnt from functions. Now let's kind of see why this works. If we consider this form that we had before, if I just copy and paste this down, for example, don't even worry what q of x is or r is. Let's just say these are just arbitrary expressions for a quotient and a remainder. If I were to substitute, say I had, for example, this was x minus 3. Now, if I substitute in 3 as my input for x, that's going to give me p of 3, with the 3 being this new input, and I have here 3 minus 3, and then q of 3, but that doesn't really matter, we'll see why in a second, plus r. Remember, the operation when we write these polynomials in factored form, there is an implied multiplication between our divisor and our quotient. Now, what that gives us is this 3 minus 3 just becomes 0, and anything I multiply by 0 is going to go away. So I'm going to be left with r. So remainder theorem tells us that when we divide by some divisor, the remainder is going to be given by substituting in something, this a value here. Substituting in this guy here. We have x minus a. So if we substitute in a to here, we're going to get our remainder. So let's just practice this for one example. Say if we have some polynomial in terms of p of x equals to x cubed minus 5x squared minus x plus 4. Sure, we can factorize this eventually, but say this was divided by x minus 2. Let's write this here. So it was divided by x minus 2, and we want to see what the remainder is. Now remember, these guys here, that is basically in the form of x minus a, where this a term, in this case this is positive 2, because it's in the form x minus a, so x minus 2, my a term is going to be 2. If I substitute this back into here, I'm going to get the remainder. So I'm going to get p of 2 equals to x cubed minus 5x squared minus x plus 4. Substituting that in place of all of these x's, I'm going to put 2. So I have 2 cubed minus 5 times 2 squared minus 2 plus 4, and that gives us minus 10. So this is how the remainder theorem works. If we say this polynomial is divided by this thing in the arbitrary form x minus a, if we substitute in that a term, we're going to get what the remainder will be. Now let's try one more on the remainder theorem, then we'll move to the factor theorem. Let's say this same polynomial is, actually let's call this part A. Part B, it's going to be divided by x plus 1. Now remember, these things are in the form x minus a. So to get plus 1, a must be negative 1, because x of minus 1 is going to give me x plus 1. So in this case, our a equals to negative 1. And that's what I'm going to sub in to my polynomial equation. So I'm going to get p of negative 1, I'm substituting that in for my a, equals to negative 1 cubed minus 5 times negative 1 squared minus negative 1 plus 4. And once you put that into your calculator, you should get negative 1. So therefore we can say our r, our remainder, is negative 1. This is what our remainder theorem tells us. It gives us a really good way of, before even dividing through or whatever, checking what the remainder is going to be, what we're going to expect. And it's based on this thing that we showed up here. Okay, now I forgot to write this here for this guy, because at the end of the day, what we're trying to find is the remainder. That's what our remainder theorem is trying to show us. Okay, let's look at factors this time. So this is the factor theorem. Now, just thinking about this, when you actually divide something through, to say something is divisible by another thing, so we say, for example, 6 is divisible by 3. What does it actually mean to say that something is divisible by another thing? Well, that means that when you divide 6 by 3, you are going to get, you're going to get a number that, you're going to get an integer basically. A number that goes into it really nicely where there is no remainder. So you go 6 divided by 3, that gives you an answer here. We can say 3 goes into 6 really nicely. We're not getting a fraction or decimal or whatever. We are getting a nice number. There is no remainder here. It goes perfectly into it. Whereas, for example, 6 divided by 4 is going to be 1 with a remainder of 2. So this means that our 3 is divisible, or 6 is divisible by 3, 6 is not divisible by 4, so the remainder is going to be 2. In other words, this is kind of subtle, but let me just write it in here. We can say that if something is a factor, it has a remainder 0. So if we go back to this thing up here, if this guy was divisible by x minus 3, the remainder should actually be 0 if it is indeed a factor. So this is important when we actually try to apply this. So if we look at the factor theorem, our factor theorem tells us that if, or I should say when p of x is divided by x minus a, sorry, that's shocking handwriting, by x minus a, and the remainder is 0, let's say, well, in essence, p of a equals 0, then this is a factor. Hence why it's called the factor theorem. Then x minus a is a factor of p of x. And let's test this with a couple of examples. So we're trying to determine whether the divisor that we're taking is going to divide really nicely and give us no remainder, and in other words, it's a factor. So example 2, we're going to consider the polynomial p of x equals to x cubed plus x squared minus 3x minus 6. So for part A, we're going to see if x plus 1 is a factor. So remember, since these are in the form of x minus a, therefore we can say in this case, like our previous example, a is going to be negative 1. So we're going to write in p of negative 1, and if the output, what we get out once we substitute negative 1 in for all of these, if this gives us a 0 term, well, if this gives us a 0 output, then we can say that this is a factor, that x plus 1 is a factor. But once we do this, we are going to get that this equals negative 3. So this will in fact have a remainder of negative 3, but here we can say that x plus 1 is not a factor. Okay. Let's check another example. Let's check x minus 2. So similar one as before, and because these are in the form of x minus a, here a is going to equal to 2. So I want to test p of 2. So I'm going to put my input of 2 in everywhere I see an x. So I get 2 cubed plus 2 squared minus 3 minus 2 minus 6. Oops, sorry, positive 2. And once I put this in, that's going to give me 0. So we can say, therefore, x minus 2 is a factor. A number is a factor of another if when you divide through, the remainder is 0. Okay, let's look at one more trickier, I should say, example. Here we are going to apply the remainder theorem to solve a more abstract question. So this is saying we're considering, in question 3 here, the polynomial p of x equals to x cubed minus x squared plus 2x plus k. We're asked for what value of k will p of x divided by x minus 1 have a remainder of 5. Sorry, yes, of 5. Okay, so let's just check what the question is actually telling us. So here we have our polynomial, and it's getting divided by this divisor here. So for our divisor, x minus 1, our a, let's do this in a different color, our a here equals to 1, because these divisors are in the form of x minus a. So when we get given a question like this and it's a little bit confusing, what we do is we just stick with what we know first. We write down everything we know, and then we try to work our way through it. Now this is saying that a remainder of 5 will be given when 1 is substituted in for all of these x's. So we're just going to, this is going to require us to set p of 1, because remainder theorem tells us when you substitute in this a value, it will give you a remainder of 5. Now, p of 1, this guy here, is just going to be this thing on the right-hand side with 1 substituted in for all of the x values. So let's actually do that. Instead of p of 1 on this left-hand side, I'm just going to substitute 1 in place of all of the x's. So I have 1 cubed minus 1 squared plus 2 times 1 plus 5. Oops. Sorry, no, plus k. Apologies. That is what we have up here. And that is going to equal to 5. Because that is what the remainder theorem tells us. Okay, now this just becomes a matter of cleaning this up. So these two are going to cancel out. 2 times 1 just gives me 2, plus k equals 5, and now this is a pretty simple one-step equation that we already know how to solve. So k is going to equal to 3. But this is how we can start to apply the remainder theorem, and we can apply the factor theorem in the exact same way for questions like this. You just take what you know and we set up an equation to solve for this particular unknown that we are trying to find. That brings us to the end of the video. Thanks so much for watching, and I'll see you next time.